Welcome to the Chapter 14 pre-lecture video. The main focus for Exam 2 material is going to be around two major formulas, the expected value and the standard error. And there are three different types of expected value or standard error. We have the sum, which we've become familiar with in previous lecture, the expected value and standard error of the average of a box, and the expected value and standard error of the percentage of a box. So, what exactly are these last two main ideas that we are unfamiliar with? And I figured there's no better way to learn than to just jump right into an example. So let's start out just with building a box. Carly, Wenley, can you build my box for me?
Sure.
So, can you throw out some numbers for us?
Oh, 2.
Okay, we got a 2.
-5.
Okay, a -5.
Oh, 6.
And one more.
5.
Perfect. So we have a box filled with 4 different numbers. And let's just get some basic statistics on this box. 2 plus -5 plus 6 plus 5 divided by 4.
That'll give us the average.
And the average of that box is 2. So we have an average of this box is 2. And the standard deviation of this box, I believe, is 5?
Yeah, 5, right?
About 5. Almost 5.
Okay, so there are just some basic facts that we're giving to you, that we're providing to you. So we have our box, we have our average, we have our standard deviation. So, next thing we need is a number of tosses, a number of pulls from this box, our n. What should we call our n?
100. Let's just see.
And not 100, a nice solid number. So we have basically all of these major pieces of information that we need to get to our expected value and standard error. So let's first start with the average of the box. So what does this mean? If I were going to pull out tickets and replace them each time, 100 times, I'm pulling out tickets, I'm keeping track, adding up the numbers, adding up the numbers, adding up the numbers, and then when I'm done, I divide in order to figure out the average of my pulls, right? So, the expected value of my average of the box, well, if I were to pull from this box 100 times, do you think I'd see, just a lot of 6s or a lot of -5s? I mean, what do you think the makeup of those pulls would be?
I think it'd be around the average, right? Because we wouldn't really see the extremes of both ends, like the smallest and the biggest numbers in the box.
I agree. I think that for each pull that we're doing, I think we'd get a pretty fair representation of the contents of the box. So it would be a likely assumption to make that the average of these 100 pulls from that ticket would correspond quite nicely with just the average of that box, right? So here we are talking, and it seems like there's not even a formula for this. So the average, the expected value of the average of the tickets I'm pulling out of a box and then adding up and dividing in order, to find the average of my pulls is probably going to match up very well with the average of the box. So we can just assume the average, the expected value of the average of a number of pulls is going to be equal to just that of the average of the box. So really, don't even worry about a formula for that, right? Just use your common logic, your common sense. Does that seem to make sense to everybody?
Mm-hmm.
Does it matter if we're drawing from the box a different number of times? If we had a different n, would the formula still be?
That's a
just
great
the
question.
average?
If we pulled 10 times, 100 times, 1,000 times. I think if this was truly a chance process and the contents were fairly mixed in this box, we would probably still see this equal representation of the extreme high and low end numbers and then of those middle numbers. So I think we would come out with a pretty nice round average. So the answer is, if n was 10, n was 100, or n was 1,000, the average of the expected value of my average of those 3 different n's would still be the same. That's a great point, Carly, that the average, the expected value of my average is just going to match the average of the box regardless of how many times we're pulling. Does that make sense?
Yeah, that
Yeah.
makes sense.
Now, Carly, you want to walk us through the standard error of the average?
Sure. So the standard error of the average, we know from before that the standard error of the sum is just the square root of n times the SD of the box. So what do you guys think would happen if we're trying to take the standard error of the average? How do we find the average? What do we usually do when we're trying to find the average?
Just add up each ticket, right, and then divide by the total number of tickets.
Right.
Exactly, and divide by the total number of tickets. I think that's the important part. So here, all we're doing is taking that SE of the sum formula, which is the square root of n times the SD of the box, and dividing by n, the number of times that we're drawing from the box. And if we simplify this formula, we get exactly what we have over there in blue by Jackie. The standard error of the average is just going to be equal to the SD over the square root of n, since the square root of n over n just simplifies to the square root of n.
So because we're dividing, does this mean that our standard error of the average is going to be smaller than we would if it was the standard error of the sum?
Yes, exactly.
And
It's
that,
like they're doing opposite things, right?
that makes
One's
sense.
bigger,
Yeah.
One's getting smaller.
So in this one, we're multiplying the standard error of the sum, because sums, we're taking the sum of numbers. And in this one, the standard deviation of the, or the standard error of the average, we're dividing, so it makes sense that it's gonna be smaller than the standard error of the sum.
So the greater number of pulls I have for the sum, the greater my error is probably going to be. While on the opposite end of that, the more times I pull from a box, the smaller my standard error of the average is going to be, because I'm probably going to be getting closer and closer to that average with each pull. While over here, I'm just going to be adding more and more wiggle room. Each pull is going to add more error. Does that seem to make sense?
Yeah.
Great. Well, so that takes it for the that covers the average of a box. Should we calculate it for this box here?
Sounds good.
And I'll get rid of that purple marking up. Here we go. Carly has the beautiful handwriting here. So if we were to calculate the expected value of the average, I pull out my calculator. I'm going through my list of formulas, and I find there is no formula, right? Standard error, the expected value of the average is simply the average of the box. So there's really no work required for this one. If I were to pull 100 times from this box, I would expect the average of my pulls to match the average of my box. So the expected value of the average is 2. And how about that standard error of the average?
So now we're gonna take the standard deviation of the box, which we're given is 5, and divide that by the square root of n. Our n is 100, so the square root of 100 is just 10, and we get the standard error of the average is just 0.5, or 1/2.
Perfect. So Carly just demonstrated how we calculated the standard error of the average. And we said that that was going to be 5 divided by the square root of 100, which is 10, and that got us 0.5. Let's compare that standard error of the average to the standard error of the sum, which we had expected this would be a lot smaller than that. So the standard error of our sum would still be that square root of 100, which is 10. But now this time, instead of dividing, instead of there being division, we're using multiplication. So the SD of the box is still 5. So the only difference between these two formulas in purple is this one we're multiplying, making it greater, and this one we're dividing, making it smaller. And so we would get 10 times 50. 10 times 5, which would get us 50. So just to compare, our standard error of the sum is much larger than the standard error of the average, which is just what we expected. The more times we pull, our standard error for our average is going to get smaller and smaller. The more times we pull, the standard error for our sum is going to get larger and larger. So Wenli, how would we continue calculating the expected value of the percent from here?
All right, so for the expected value of the percent, we're just looking at the percent of ones in the box here, which is like finding the average of the box. So, let's see, there's only one ticket with a 1 here, so that corresponds to 1 in the numerator, and we have a total of 4 tickets. So we have 4 in the denominator.
So one of what we're looking for out of 4 total tickets.
Yep, so
Gotcha.
that's equal to 0.25. Right? So, we have 0.25, but we want the percent in the box. So, to transform this, it's just multiplying by 100.
Right. So you take basically the average of the box and multiply by 100. That sounds good.
Yep. And that equals 25%. Just leave it out here.
Sure, 25%. So that means if I were to, similar to the problem earlier, if I was to pull 10 tickets or 100 tickets or 1,000 tickets, I would expect my pull to have about 25 ones in it, or 25 negative
Negative
numbers,
numbers.
since that's
Yep.
what we're looking for.
Exactly.
Right.
Okay, so we just saw that the expected value of the average is essentially the same thing as the expected value of the percent, except the expected value of the percent is in percent form, so it's 25%. So now, when we look at the standard error of the percent, it makes sense that if you look at these two formulas, the standard error for the average and the standard error for the percent, they're the exact same thing, except for the standard error of percent, we have to multiply by 100 to get it in that percent form. But essentially, they're exactly the same thing. So now, let's go ahead and calculate the standard error of the percent of ones in this box. So, first, we need to take the standard deviation divided by the square root of n. So we need to calculate the standard deviation of this box.
That's a nice shortcut for that, right?
Yeah.
Now, why aren't we using the standard deviation of 5 that we were given earlier?
Well, this box and this box, while they're kind of representing the same thing, they're also different. This one has different numbers, 2, -5, 6, and 5 on the tickets, and this only has zeros and ones.
I see. So new box means a new average and a
And
new
new
SD.
SD.
Right.
So what are we going to get for this new SD? What's that formula that we learned before?
Well, it's the absolute value of the difference between your two ticket values, so A minus B.
Okay, so we have zeros and ones for our tickets, so let's
Good.
just do the absolute value of 1 minus 0.
Good?
Yep, times the square root of the proportion of tickets that we have labeled 0 and 1.
All right, so first of all, what's the proportion of tickets labeled 0? We have 3 tickets that are zeros.
Out of 4 total.
Yeah, so just 3 over 4.
So 3 out of 4 are not what we're interested in.
And then how many are ones?
1 out of 4.
1 out of 4.
And the total under the square root sign always adds up to 1 as a good way to check your answer.
Yeah, so if we added 3/4 plus 1/4, we'll get 1. So when we calculate that SD, we end up getting 0.44 if we
Okay.
multiply all that out. So now we're just going to plug that into our formula for the SE percent. So again, it's the SD, which we got as 0.44, divided by the square root of n. Our n, remember, was 100, so the square root of 100 is just 10. And then we're going to multiply that by 100 to make sure that we get our standard error in the form of a percent. And when we do that,
4.4.
4.4%. And exactly, it's percent. So the standard error of the percent is 4.4%.
So to put it in human terms, if I were to pick out tickets 100 times out of this box, I could expect to get a negative number 25% of the time, give or take about 4.4%. Is that basically what we just solved for?
Yes, and that makes sense.
So put these formulas away in your statistics toolbox and get ready to use them on a regular basis. Understand how they're different from each other, but how they're all related.